C++17 is out, and there are lots of people after seeing the update says that, oh, this is a minor update. There's nothing exciting, nothing actually changed the way we program. I want to say these people didn't study hard enough, because there's actually not just one thing which I'm going to talk here today. There are lots of things in C++17 that actually can change the way we program and change the way we can think program. This tiny looking feature, class template argument deduction, actually gives us a new abstraction, a new way for us to view and design interface. And before starting, I should thank Michael Spertus, who created this feature and continuously put efforts to make this feature better. And also today have made a poster outside called Class Template Argument Deduction Best Practices. I read that poster and I'm very happy about seeing it, because it covers lots of materials that I didn't cover here because I really don't have time to cover it. So please go read that poster. Now, when introducing a new feature, Herb often tells us to start with some comparison, like before, after. So yeah, with this new feature, we can now save 5 keystrokes. If you go begin and end, you say 10 keystrokes. Is that exciting? Well, actually, the second line, I should say, it doesn't always work. It sometimes cannot replace the before one. The poster made by Michael explained why. I didn't have a dedicated slide in this talk to explain why. If at the end of the talk I didn't explain it, please remind me. But let's move on. So this part excited me, because so that I can finally write C++ like a dynamic programming language, still with strong type checkings. But you don't need to specify all the types, right? It's good for both the reader and the compiler, but does that work on all containers? How about this? Well, none of them work. So I start to feel this talk is hard to continue now. It's not exciting, it's actually disappointing. So this is why the title of the talk is Class Template Argument Deduction, a New Abstraction. Let's forget about these tiny pieces. Some of them make sense after you understand this feature. Some of them will fix it in the future. But this feature itself, we need to view it in another angle. And let's start from the very basic, the language details. I'll try to explain this feature as detailed as I can, so that you can make full use of it. As you may know, the class template argument deduction consists of 2 parts. One part is automatic deduction, and another part is deduction guide, which you explicitly write out to tell compiler to how to do the deduction it cannot automatically do. And automatic deduction just gives you some default behaviors, and just like all other defaults in C++, they can be overridden, so they exist. But you need to know how the default behaviors works in order to override them. Otherwise, you end up with something like this, where every time I want to override something special member functions, I need to look at how it's slide. So what automatic deduction gives you? First, it gives you a new syntax. The syntax is an initializer followed by a type name. And the type name can, of course, be qualified. So what does exactly mean for you can use template name in place of a simple type specifier? And put it in this way: auto is a simple type specifier, which means you can almost use the new syntax class template argument deduction in places of where auto can be used in almost all places. But with plus minus some exceptions. But please understand it in that way. And how we actually do the deduction. So the following is not exactly what compiler does, but please use some imagination, just like what you do in mental overload resolution. So when you are writing this last sentence, to use the type name against the class template without providing the argument list, you can imagine that the compiler tries to move the class template parameter list down to the constructors or constructor templates and puts them together, and you immediately find that the last line starts to work, right? Because you are right now currently deducing against a function constructor template against just a class rather than a class template. So the next time if you are running into a problem how brace initialization works, how aggregate works against the in the context of class template argument deduction, just think it in this way. The compiler tries to move the original template, class template parameter list down to the function and function templates. After that, we can do the deduction, we can get the results for each parameters, and we put those parameters back to where they came from to form the specialization. In this case, it's vector car, allocator car. So we got our first rule for automatic deduction. That is, one part of our deduction candidates come from the constructor with compiler synthesized template parameter list. However, during this process, there's a tiny issue. Well, actually not tiny, but let me explain. You can imagine that previously when you are designing a class template, you expect user to manually specify the class template argument, right? You don't expect them to be deduced. Therefore, in some cases, when the compiler tries to move the class template parameter list down, it has some semantic changes, right? If you move it down here, this T ref used to be an R-value reference. Now it becomes a forwarding reference. That's the semantic changes. But fortunately, we fixed it. The standard just says that R-value reference came from class template parameter list. It's not a forwarding reference. That's it. It's an exception, special rule. Where this feature can be used, as I said, it can be used in place of auto in many places. You can imagine it's a better auto in some way. Notably, the exception includes you can use it in new with more than one argument, but you can use that with auto. And the class template argument deduction can be only followed by CV qualifiers. No ref, no pointers. And there are something I think we missed in the new standard. I hope we can fix in the future. For example, we are able to use auto in place of return type as class template argument deduction not allowed. Richard Smith already said if someone proposed to add it, it will be accepted. So you got a chance to write a new paper. For this intuitively, for the last one, intuitively you should start, say, generic lambda. I'm not sure whether it fully makes sense, but anyway. So also, in other ways, it has other ways similar to auto. Like auto allows you to declare more than one variables at the same time. With class template argument deduction, you can do it as well, and the requirements is the same. Both variables need to be exactly the same type. But when the uniform initialization kicks in, there is some difference and difference on top of difference. I'm going to explain how detailed is it, what the difference are. But I apologize that I have to introduce something not existing in the standard yet to explain the rationale. But trust me, that's the most intuitive and most clear way to remember this difference. The first thing, let me introduce some variable. Let's say it's an optional int. So auto, if you use auto to declare something with parentheses, that variable, it copy constructed, right? New auto something, it allocates on heap and copy constructed. The last thing doesn't exist in the standard yet, but you can imagine what that is. It creates a PR value by copy construct, right? Let's look at type name. Exactly the same thing. Parentheses, one argument, copy construct. If OPT is a specialization of optional, and if you use new, allocate space, copy construct, temporary, copy construct. And if we are in the case of single argument within parentheses, exactly the same thing. The colon on the left-hand side, left-hand side, all do copy construct. The colon on the right-hand side, all do auto copy construct. And we finally brought down to the difference to this one tiny piece, this one tiny slide. That is, when auto is being used against a copy list initialization with more than one argument, it creates initializer list, initializer list. And when the copy is being used with direct list initialization with more than one argument, it does not allow. But for class template argument deduction, it just works. So we got our second rule. That is, when the class template argument deduction are used against one argument, and that argument is a specialization of the class template you wanted to declare it against, it always try to do copy. So we have this new set of candidates that is a copy deduction candidate to impose this. This behavior can be overwritten. You can expand. I will explain this later. But as you see in previous slides, it may not be a good idea to do so, because in generic programming, somebody might want to compare it against auto using place auto. If they got different behavior, there will be something surprising happen. And the next, I'm going to talk about our third kind of deduction candidates, that is the default constructor. It simulates the behavior of generating default constructor for if you do not declare any, but there are a little bit difference. Let's start with how actually we use them. So in C++14, we added this transparent comparator. So that's when you are writing algorithms, you can say start begin and comparator, the diamond operator, and then parentheses. The diamond operator, there's no such thing, right? It's just an empty class template argument list. And it will use the default template argument that is void. But now we get class template argument deduction, although there's no source for deduction, but we can add this new syntax allow us to eliminate this diamond. Now we get something very close to Sean Parent's SL library. I love it. These tiny new changes. So what's the difference between compiler provided default constructor? Then there's one tiny piece of difference. You can notice that the only places where this feature makes sense is that you have a main template and default your class template parameter to point your functionality to a specialization, which means only the specialization makes sense. The main template doesn't matter. So special rule, that is, we just provide this default constructor deduction candidate even your main template is not defined. It can be just a declaration. As long as you have such a specialization, it just works. So we have finished our automatic deduction. Now let's go to the cases where automatic deduction is not enough. So take a look at this example. We have constructor template which has no t in its argument list. So you cannot deduce t out of this. What do with it? So we introduced deduction guide. Not in this syntax. It's just imagine that you have some mechanism allows you to describe what's the deduction result you want to see, and specify it in a way like a return type, and you move this thing out of the class scope. Then we got a deduction candidate. And this one is called deduction guide. The exact syntax is called deduction guide. Is just like a constructor but followed by a return type. Although this declaration is neither a function or function template. It's just a declaration. It has to appear in the scope where the class template is declared. And the last line actually imposes a restriction from my point of view here. That is the simple template ID which appears in place of the return type has to be a specialization for the class template, which means we can use a trait to compute this type and use some part matching to match it back. From my point of view, these restrictions is something deserve to fix. So far, we have done talking about our almost all the language. No, not yet. We have done talking about all the deduction candidates, and the first three are for automatic deduction. The last one is a focus for the rest of the talk. So let's move on. I'm first going to explain the interactions between these deduction candidates. More specifically, how the deduction guide interacts with automatic deduction candidates. Put it in a simple way, all your candidates are ongoing overload resolution within one overload set. What does that mean? Imagine that, how to say, let me put it in this way. When you're writing a deduction guide, you are adding new candidates for overload resolution to an existing overload set. You are not replacing any signature that is generated by compiler through automatic deduction. You are only adding it. The automatic deduction candidates are always there. They are not replaced. There are some way to suppress them, but if you do not manually try to suppress them, they will give you surprising results. Here's an example. I write this deduction guide, and based on the language rule, a deduction guide takes priority over the automatic deduction candidate when the deduction guide is at least as specialized as the automatic deduction candidates. Well, in this case, it's not just at least specialized, it's even more constrained, so it takes priority always. However, when this constraint is not satisfied, my last line is not rejected. Instead, it falls down to the automatic deduction candidates. So you cannot actually impose more constraints through deduction guide. You need some other ways to do so, or maybe just this is not a good design. For the rest of the talk, I'm going to talk about how to design rather than trying to fix these problems. But okay, let's start with going deeper. I mean, here I provide a deduction guide toolbox. Let's start with the very basic to think about what deduction guide is good for. So obviously, it's good for disambiguation because you're adding new overloads to an existing overload set. And if you ever listened or watched my previous talk in C++, now there's a talk called disambiguation the black bag technology. You will know more details about it. But look at this example. I think the ambiguation is very obvious, right? At the same position, you have camp, you have alloc, none of them is constrained. So when you're passing allocator, both answers are equally good, so there's an ambiguation. Then how to fix it? We can fix it by adding constraints on the deduction guide. So here I constrain the allocator to satisfy allocator concepts. This deduction guide is more constrained than this. Than the second constructor. So in that so that it takes priorities, and in that way this the last line compiles. The next trick is not actually a trick. Next thing is about how exactly write deduction guide, because there are some special things going on in deduction guide which can make your life easier. So let's look at this example. It's a fairly simple example, right? It illustrated that automatic deduction often doesn't work. Even for the simple cases where we just use a forwarding reference, a universal constructor, because why it doesn't work, right? Because T doesn't present here. There's only a U here, which the U is only come from the constructor template. So the last line doesn't compile. How do we make it compile? So maybe learn from make optional, which is an existing utility in the standard library. It takes argument, perfect forwarded, dedicated. So how about translate that into a deduction guide? I should say that works, but please don't do that. Try this. So Micro's poster also has this section, right? Try to use this style as much as possible. Actually, to be honest, please always use this style because it always works. Let me explain. So, if you use this to declare a function, take by value, right? It may not work because that type may not be copyable or movable. Well, neither copyable nor movable, right? In that case, it doesn't work. However, deduction guide only perform overload resolution, which means it only queries your type to see whether it can get involved in overload resolution in a context where copy construction is desired. And it happens to be the case that in C++, all types can get into overload resolution, participating in overload resolution for copying. Just look at this slide, look at the highlighted column. There's no slot that says the copy constructor is not declared. The copy constructor declaration is always there, even you deleted its body. If deleted body, it doesn't change its nature, that it can participate in overload resolution, and the result is that all type have the potential for being copied. So I change the font size here. If at the end of this talk you forget about everything else, please remember this piece. Just use this style, take by value in overload resolution. It's not just because this style is simpler. It's because that's a part of the essence of this deduction guide. It's the first utility in C++ that splits the overload resolution from the function application. When previously we were writing function when we were writing overload set, one difficulty is that the overload resolution is tangled with the actual application. That is, if you look at the pair signature in the standard, there are how many? There are 32. They are all there for tweaking the actual application, the way of actual application. But deduction guide gives us this chance to specify the overload resolution in one place and do the actual function application in another place. And it comes with lots of other benefits. For example, it replaces all the copy-like signatures. These are all the possible signatures you can impose on a copy constructor and move constructor, and there are more. They can be CV qualified. I don't even include the volatile here. But this one signature that take by value covers all of them. And actually, in the core language, the copy deduction candidate is written using this style. So the language itself is also using this style, which imposes the copy deduction candidate imposes a new candidate out of an invented constructor, CC, where C is a class template name. Not just the language uses it, the library also uses it whenever possible. We use this style on pair, tuple, array, or the tuple-like types. So the next tool in our toolbox is how to suppress an automatic candidate. As we previously discussed, the deduction guide are good for disambiguate, not good for adding new constraints, because the existence of the automatic deduction candidate, when you're writing deduction guide, you have to make your deduction guide, if you constrain them, you need to make them mutually exclusive. Now that comes with a problem. What if some parts of the results I don't want? How do I suppress the results produced from automatic candidates? Intuitively, you may want to use -delete to do so. However, that syntax is not yet allowed for some reason, because if you are very familiar with C++, then -delete is a definition, not just a declaration. But let's forget about that. We can simulate that. You don't want the result, right? Just give it a garbage result. Now, since we can suppress one deduction, automatic deduction candidate, is that possible to suppress all automatic candidates? Well, yeah. Step 1, rename your existing class template parameter to something else. Step 2, redefine it to identity. If you are unfamiliar with identity, that's its code, but it basically says put this type in non-deduced context. Therefore, all the automatic deduction candidates involved are suppressed. Now, why you want to do so? Well, from engineering point of view, maybe because you have seen lots of surprises, in previous slides. Sometimes you require fixes to fix automatic deduction candidates. And you can imagine that if one user starts using your library and they start to rely on one automatic deduction, and some other user send a bug report says that deduction doesn't make any sense, and you later want to use a deduction guide to fix it, the impulsive breaking change. This trick can be used to fix that problem, because you can just try to ship your library with all deduction candidates disabled at first place. Maybe later we can fix that if we have time. But more important thing to us is that you got a chance to override any automatic deduction candidate. Because actually not override, but semantically override. The deduction candidates no longer exists. So you can think it in an overload resolution way, right? The first step in overload resolution is to try get all the, try match the arguments position by position. Like if your function takes 3 arguments, you're passing 2 arguments, obviously it doesn't pass overload resolution. That's the first step. So with all the automatic deduction candidates disabled, we can now override the automatic behavior caused by constructors in a position by position basis. Even though you see T is obviously not a specialized size T. And it can enable many tricks after disabling when writing deduction guide, like the priority tags, the ... trick, and more. If you are not familiar with this, I don't have time to explain it, but because that will be another talk, let's move on. If you are interested, ask whoever library implementers you're familiar with. So the last in our toolbox is that you can dictate the type you want to deduce. Let me finish this example and why this is important. So here is an O-string joiner. This example comes from the library fundamental TS v2. Well, this one is just a much simplified version. So with O-string joiners, it first takes an O-string and next take whatever as a delimiter, but there's an issue. Somebody may think it is an issue, is that if it takes a pointer to an array, what if later the array content changes and my O-string joiner changes as well? It may be a problem to some people. How about fix it by imposing string here, so that you store this delimiter? Somewhat reasonable, right? And it turns out we can fix this with a deduction guide, like this. You just say that when the input is a pointer to a character array, we deduce to string. That syntax, if you are not familiar with that syntax, let's go back and take a look at our deduction guide syntax. The deduction guide is merely a declaration. It doesn't say that it has to be started with a template. If you are familiar with how template work in C++, a template is just a declaration prefixed by a template head. If declaration is then using, then that becomes an alias templates, things like that. Deduction guide is the same thing. By itself, it's still a deduction guide. You can use it to point concrete types from one to another. Now, with this thing, it's like you are forcing. I'm using the term invites here. You are inviting an implicit conversion from the character array to string. Can that be still called deduction? Like when doing function template parameter deduction, you won't run into the case that is, while you are doing deduction, you are also having an implicit conversion, right? That is why I use the term dictate here. You're saying that I just want this result. So if you try to understand this example more deeper, you will realize that the second essence of deduction guide is that it's not deducing. It gives you an ability to select a specialization for a given overload resolution. So when in the next section of our talk, the last section, I'm going to say that how we make use of this essence. Do not try. Your work is not done after you deduced something. Your work is just started. I want you to think about which specialization you want instead of what template arguments you want. Think about the deduction guide as a whole. Pick your specialization before you're writing a deduction guide. I call it design by having class template argument deduction in mind. So what do I mean by design? Let's look at this example. So I say this is a bad style, right? How people come up with this bad style? Obviously, they didn't think about the specialization as a whole. They merely copied this thing from make optional, right? If I design this deduction guide, this is what I'm going to do. Like, user asks me, hey, your optional OPT equals 42 doesn't work. Okay, pick your favorite specialization. I want optional int. Here's your deduction guide. Does that solve the problem? Are you kidding me? Okay, maybe I need to add more deduction guide. So now I have optional int to optional int, optional char to optional char. Generalize those into optional t to optional t. So you just got your idiomatic deduction guide, right? It's not, this style is not invented, it's just intuitive, based on user requests. We call this design. You don't copy from something existing, just think about what result you want, what result the user want. It's just like, business management, do marketing, ask for use cases, and use some innovation. But the innovation here in C++, in class template argument deduction, we mean generalize it, make things larger, specialize, make things more focused, right? And do this again and again. Now, this is how I design a deduction guide. Now let's go to the next question. Why I say this is this is a new abstraction. You are just not designing one deduction guide. You're actually designing a whole class template. So why you are writing a deduction guide? Like previously we discussed several cases, like to fix a bug, disambiguation, to add some new feature, like enable a non-deduced case. But how I can tell you that by writing multiple deduction guide, it can give you a class template a new interface. Essentially, the class template algorithm deduction, what it gives you is a new interface. This interface is a template name followed by parentheses or some initializer arguments, ... right? It's an interface for your entire class template, because it doesn't say it's specialization. It's an interface for your whole class templates. It can involve all specializations. So here's an example of how to make use of that. The design flow is similar to before. So here's an use case. Let's say we have a my vector with an allocator as a template parameter. If you are familiar with regular type, you may find that this design is not very satisfactory because it imposes policies in its type so that a vector of different allocator can't even be compared. But the salient property of the two vectors are merely the values while you want to compare the allocator. That if you replace the question mark with equal, that doesn't even compile because they are different types. So that is we have this polymorphic allocator. Its purpose is to solve this problem by eliminating this piece of type information out of your container. Here I'm using an allocator design that's different from what exists in standard library, but let me continue. Let's say we have a polymorphic allocator, that's a base. And you have pull allocator derived from it, new delete allocator derived from it. And let's look at our previous example again. Damn it, that still doesn't compile. Even you defaulted your template, a class template parameter to polymorphic allocator, because automatic deduction candidates deduce those into two different types. Again, design it. What's your favorite specialization when seeing this vector followed by a initializer list and some allocator? Just the base class. Here's your deduction candidate. Problem solved. But in this case this example requires to express all the automatic candidates first. If you are a overload resolution expert, you will know immediately why, but I don't have time to explain why here. Oops. Okay. So, what do I mean by new interface then? The new interface is for the whole class template, right? Think about this. Nobody writes this, right? Nobody writes code like this. The template parameter lists are not designed for people to manually fill in this class template parameters. if you write this, you I don't know how to describe that, but you can imagine that type of interface exists. That type, I mean, that an interface designed only for deduction. Does that make sense to class template argument deduction? Yes, but this is totally experimental material. Don't try it at home. Well, you can try it at home. Don't try it at your company, I should say. So just like you write multiple specializations, multiple overloads, hidden specializations for your class templates, we reverse the process. We can choose to not write deduction guides for the class template, but instead we build with specialization to implement the interface we create with deduction guide. We imagine that we have the interface first, and we use some specialization to implement it. So look at this example. So the vector ball problem is sort of well known, right? Theoretically, we have a chance to fix it by imposing a type tag. The real bool tag doesn't have to be a bool like anything. It's just there for picking a specialization, give you a place to build that specialization, and then you can build this specialization with real bool. Therefore, fix the problem. Somebody might say that doesn't always work because when no arguments is passed in, how to deal with this? Well, that's not unsolvable, right? With Boost HANA, you can use value type and deduce from value type. So theoretically speaking, we really have a new interface. That interface doesn't require to pass any explicit class template arguments at all. We can only stick with this new interface if you want. Maybe this can be improved in the future standard. We have some new syntax to allow you optionally to fill in some type parameters. But the door is already open. The possibility is already here. So conclusion. I just want to say one sentence. Try design your entire class template as one overload set. Don't try to fix bugs. Don't try to design a deduction guide solely. Put them together. Start from looking at what syntax, what result you want after reading a given syntax. Question time.